My name is Aidan McFarlane, and this is the physics of volleyball. The first step I used to collect data was run a trial on the relationship between distance and time of an underhand serve of a volleyball. To do so, I had Trevine run 4 trials where he served the volleyball underhand from the same place. Using a measuring tape, I calculated the distance the ball went, and using my phone as a stopwatch, I calculated the time it took to hit the ground. Using a digital mass scale, I found the mass of the ball was 0.28 kilograms. Kinematics. Kinematics is the study of motion of all objects without regards to the mass of the object or the forces acting upon it. By investigating the kinematics of the underhand serve, I can identify the acceleration and speed of the ball. Speed is represented by distance over time. The maximum speed occurs right before the object hits the ground. This is because after the projectile reaches its peak height, the ball works with the acceleration due to gravity, causing it to hit the ground faster. The max speed can be found using the equation v2 squared is equal to v1 squared plus 2a delta d. Acceleration is the value for any object whose speed/velocity is changing. Acceleration is represented by speed over time. Since the ball starts at rest, 0 meters per second, when in the server's hand, the ball must accelerate to 7.35 meters per second, the speed that the ball leaves the hand of the server. Using these speed values that I know from the data and respective calculations, I can find the change in speed, delta v. By slowing down the video, I ascertained that the ball was in my hand for 0.12 seconds. Now with both of the required values, I can substitute them into the formula to solve for acceleration. Therefore, the instantaneous acceleration of the volleyball when served is 61 meters per second squared. Projectile motion. A volleyball serve is an excellent example of projectile motion due to the parabolic arc that is made by its motion. There are 4 constants in projectile motion that can be observed in a volleyball serve by breaking it down. Constant number 1. The volleyball will always travel with a constant horizontal velocity. Upon the ball leaving the server's hand, the ball has no horizontal acceleration, meaning that it has a constant speed. By using the speed value that I calculated earlier, I can use trigonometry to solve for the horizontal velocity component. Constant number 2. The horizontal and vertical components of the projectile are independent of each other except for the time it takes for the projectile to land. Even with these independent pieces, the horizontal and vertical components follow the same motion pathway. This results in the ball landing with the vertical and horizontal components ending at the same time. This is evident when a volleyball lands and the volleyball doesn't continue its horizontal motion, so it doesn't speed away along the ground. Constant number 3. Throughout the projectile's motion, it will be under the effect of acceleration due to gravity, 9.8 meters per second squared down. This means that when the volleyball is hit into the air and no longer is being held by the server's hand, it will begin to decelerate, causing the ball's upwards velocity to decrease. This continues to occur throughout the flight of the volleyball, causing a phenomenon known as maximum height to occur. The maximum height occurs when the ball's vertical velocity is exactly 0 meters per second. After the maximum height, the speed continues to decrease due to the downwards acceleration. So the ball dips and starts to gain speed in the downwards direction. This causes the volleyball to travel back towards the ground where it will eventually land. Without the acceleration due to gravity when I hit the volleyball, it would keep moving upwards and would never come back down. By applying this concept, I can solve for the vertical component of the projectile speed. At maximum height, the speed is 0 meters per second, which means that it can be used as the v2 as this is the final speed at max height. With this, I can solve for the max height by substituting the vertical component speed as the v1 and putting the rest of the values into the formula. Constant number 4. Since both the vertical and horizontal components act independently of each other, each component has its own crucial role. The vertical component affects the volleyball by moving it vertically and causing it to have varying heights. The horizontal component affects the motion of the volleyball by causing it to move horizontally, which gives its parabolic characteristic. Forces. A force is a push or pull that occurs when the object interacts with another. The reason anything moves is because a force is being applied onto it. Using this logic, forces are highly relevant to volleyball. This is because forces and Newton's 3 laws of motion are exhibited through every hit of the volleyball. Newton's first law of motion states that when the forces acting on an object are balanced, the net force of an object is 0. The object will remain in its constant motion or its state of rest. Whenever a volleyball is hit, its motion tends to mimic that of a projectile. According to the constants of projectile motion discussed previously, the horizontal speed of a projectile remains the same throughout. Applying Newton's first law, the horizontal speed of the projectile is constant because the net force is 0. The reason the ball doesn't travel horizontally forever is because the vertical net force is not 0. This can be equated to the force of gravity which acts on the volleyball. This force of gravity places a vertical acceleration of 9.8 meters per second squared down onto the volleyball. Without the normal force exerted by the server's hand to keep the ball off the ground, the force of gravity will pull the ball down to the ground. By using the mass of the volleyball, 0.28 kilograms, and the acceleration due to gravity, 9.8 meters per second squared down, it is possible to solve for the force of gravity acting on the volleyball. Newton's second law states that when the net force acting on an object is not zero, the object will have some form of acceleration. When serving the volleyball, this is exhibited twice. The first way Newton's second law is demonstrated is the vertical of the volleyball's path. Because the vertical component does not have a net force of zero due to the force of gravity, it accelerates downwards. Newton's second law can also be observed when the volleyball is being hit. When the volleyball is being served, there is a force that is being applied onto the volleyball by the server. This causes the ball to accelerate to the point where it has a speed of 7.35 meters per second, which is speed when it leaves the hand of the server. By substituting the instantaneous acceleration and the mass of the volleyball used, I can find the force being applied onto the volleyball. Newton's third law states that for every action force, there will be an equal and opposite reaction force. Newton's third law occurs often during a volleyball game. This is present when the ball hits the floor after a hit. The ball is flying at a high speed towards the ground, so the question is, why does the volleyball bounce back up? This is because the volleyball exerts a force onto the floor upon contact. Using Newton's third law, the ball exerts a force onto the ground, causing the ground to respond with an equal and opposite reaction force, rising back up. Force of friction. The force of friction is a force that occurs when there is a contact between two surfaces. The force of friction works against the motion of any object under the aforementioned conditions. When I serve the volleyball, there is contact between my hand and the ball, thus there is friction. In order to be able to solve for the force of friction, I needed to solve for the coefficient of friction. I did so by standing by a wall in my house and holding my arms out straight with the ball laying on top of my arms. I marked the height of my fingertips and my shoulder and then slowly raised my arms until the ball began to move. I then marked the point where my fingertips were. By connecting these points, I was able to create a right-angled triangle. Using trig ratios, I solved for the angle that my arms made. Then I took the value for theta and plugged it into the equation for coefficient of friction. Using this value for coefficient of friction, I subbed it into the force of friction equation. Energy. Energy is the ability to do work. Since energy is required to make objects move, energy is crucial to volleyball. Every time the volleyball goes over the net, energy is in play. Work. As previously described, energy is the ability to do work. But what is work? Simply put, work occurs when a force is applied onto an object and it moves. Work can be solved for by using the equation for kinetic energy as a change in energy occurs. Power. Power is the work that is done on an object. Since I calculated work earlier, and I know that the time the ball was in my hand was 0.12 seconds, using the equation for power, I can sub in these values to solve for it. Energy conservation. The law of energy conservation states that energy cannot be lost, rather it is transferred between other forms. This means that in a closed system, total energy remains constant. An example of a closed system is the underhand volleyball serve I chose to collect data for. In the system, there are two types of mechanical energy, kinetic and gravitational potential. When the object is at a height that is greater than 0 meters, it will have gravitational potential energy. Since the ball is served from my hands, it has an initial gravitational potential energy. Since the ball is served from about a height of 1 meter, I can solve for this. When added together with kinetic energy, I can solve for the total energy in the system. Since this energy is constant throughout the serve, I can represent the transfers in energy required to do the serve and throughout the serve using an energy transformation diagram. The energy begins in our body as chemical energy, which is made possible by cellular respiration. It is then transferred into kinetic energy as I move my body to hit the ball. Some byproducts of this are sound energy that is heard when I make contact with the volleyball, and heat energy due to friction. As the ball ascends, the kinetic energy makes way for gravitational potential, as the height is increasing, causing an increase in Eg, and the speed is decreasing, causing a decrease in Ek. Due to the force of gravity, the ball peaks and then begins to fall back down towards the ground. Ek increases as the speed increases, and Eg decreases as the height decreases. The next energy transfer diagram represents the transfers in energy when the ball is bounced. The original energy form is purely gravitational potential energy, as it is held at a height of 1 meter and is being held at rest. Then when the ball is dropped, it is a mix of EG and EK as the height begins to decrease and the speed increases. When the ball hits the ground, there is no EG and it is all EK. In addition, byproducts of this contact are sound energy and heat energy from the friction between the ball and the ground. The ball bounces back up to its height where it is once again all gravitational potential energy. Equipment. The main piece of equipment used in volleyball is court shoes. These shoes are similar in appearance to running shoes, but have a few key differences that allow the athlete to reach their maximum potential. Firstly, the shoes have reinforced toes and firmer soles. The biggest difference is the shoe grip. The shoes have a greater grip, causing the force of friction experienced between the shoes and the court to be greater. This greatly improves the athlete's performance in many ways. Firstly is the increase in agility that is attributed to an increased friction. Because the shoes slip less, the players can have a harder push through their shoes, allowing them to stop, turn, and accelerate much more efficiently. Also, because they slip less, the athlete can cover more distance in less time, and since speed is the ratio of distance over time, they have a greater speed. Lastly, Newton's third law is shown. This is because since the shoes have a greater friction, they are more static. This means that when a player goes up for a jump, they can put more force into the ground. This results in a greater reaction force pushing them into the air.